Tonight, we're going to explore what would happen if a spacecraft left Earth in 2026 and began traveling toward the center of the Milky Way. Its destination would be Sagittarius A star, the supermassive black hole sitting at the gravitational center of our galaxy. It contains roughly 4 million times the mass of the Sun, and it lies approximately 26,000 light-years away. By the end of tonight, you're going to understand why reaching it would require more than a faster spacecraft. It would require a machine capable of surviving longer than nations, languages, and perhaps entire species. The first answer seems simple. A light year is the distance light travels in 1 year. So light leaving Earth in 2026 would reach the center of the Milky Way around the year 28,026. That is the absolute minimum travel time allowed by known physics. Nothing carrying mass can reach the speed of light. Every spacecraft, probe, or crewed vehicle must take longer. Voyager 1 is currently traveling away from the Sun at approximately 17 kilometers per second. It is the most distant human-made object ever launched. If it could somehow turn toward the galactic center and maintain its present speed across the entire journey, it would take roughly 458 million years to arrive. The Earth itself is only about 4.5 billion years old. A Voyager speed journey would consume roughly 1/10 of that entire span. Parker Solar Probe has traveled much faster. During its closest passes around the Sun, it reaches approximately 690,000 kilometers per hour. That is fast enough to cross the distance between Earth and the Moon in a little more than half an hour. But even if Parker could maintain that record speed while traveling directly toward the center, which it cannot, the journey would still require more than 40 million years. A spacecraft moving at 10% of the speed of light would reduce the crossing to approximately 260,000 years. At 20% of light speed, it would take about 130,000 years. That is the speed proposed for tiny laser-driven spacecraft concepts weighing only a few grams. Even then, the journey would last longer than Homo sapiens has been building cities, writing books, or recording history. Given those numbers, it might seem that this is simply a problem of speed. Build a sufficiently powerful engine, accelerate the ship, point it towards Sagittarius, wait for it to arrive. Yet the real journey would be much more complicated. The spacecraft would not begin from a stationary platform. Earth is moving around the Sun. The Sun is moving around the Milky Way at more than 200 kilometers per second. Any ship leaving Earth would inherit that enormous sideways motion. It would already be traveling around the galactic center before its engines even started pushing it inward. The ship would also need to cross thousands of light-years of thin gas, plasma, radiation, magnetic fields, and microscopic dust. At ordinary spacecraft speeds, a grain of dust is a minor hazard. At a meaningful fraction of light speed, the same grain could strike with explosive energy. The vehicle would need power systems, computers, shielding, navigation equipment, and repair machinery capable of functioning across thousands of years. A crewed ship would need to preserve air, water, food, health, knowledge, and social stability for longer than any human society has ever survived. And after placing an almost unimaginable amount of energy into the ship's motion, the engines would need to remove that motion again. A spacecraft that reaches the center at 20% of light speed without slowing down has not truly arrived. It has only passed through. The black hole has no surface on which the craft could land. A successful mission would need to enter a controlled orbit somewhere near Sagittarius A star, remaining far enough away to survive while close enough to study the environment around it. There is another complication waiting much later in the journey. At speeds approaching the speed of light, the clock aboard the spacecraft would no longer agree with clocks on Earth. Tens of thousands of years could pass here while the travelers experienced far less time. That effect could make the journey fit inside a human lifetime in theory. It would also demand speeds and energies far beyond anything humanity can presently produce. Before we continue, if you enjoy calm journeys through the deepest parts of space, take a moment to like the video or subscribe. It is a simple action, but it helps this channel reach more curious people who enjoy exploring these questions with us. Now, the distance to the center is only the first layer of the problem. Before a spacecraft could travel there, humanity needed to determine where the center actually was. For most of history, astronomers could not see it. The central Milky Way is hidden behind enormous clouds of dust that block visible light. The destination was buried inside the brightest part of our galaxy, yet concealed from every ordinary telescope pointed toward it. Finding it required astronomers to stop looking for the center directly. They had to trace the objects surrounding it, listen for invisible radio waves, and watch stars orbiting something that produced no light of its own. Dust made that search far more difficult than the distance alone would suggest. When we look towards Sagittarius, we are looking through a large part of the Milky Way's disk. That disk contains enormous clouds of gas mixed with microscopic grains of carbon, silicates, and frozen material. Visible light strikes those grains and is absorbed or scattered away before it reaches Earth. The result is a set of dark lanes cutting through the bright band of the Milky Way. Behind them lies the central region of the galaxy. Astronomers could see where the hidden center ought to be, but ordinary telescopes could not show them what was there. The first useful map came from objects far above and below the dusty disk. In 1918, American astronomer Harlow Shapley studied globular clusters. These are dense, roughly spherical collections containing tens of thousands or even millions of old stars. More than 150 globular clusters are now known to orbit the Milky Way. Shapley estimated their distances using variable stars, stars whose brightness rises and falls in a regular pattern. Once the true brightness of a variable star is known, its apparent faintness can reveal how far away it is. Shapley plotted the clusters and found that they were not arranged evenly around the Sun. Their distribution gathered around a distant region in the direction of Sagittarius. The solar system was clearly far from the middle. His distance estimates were imperfect, partly because interstellar dust had not yet been understood properly. The larger conclusion survived. The Milky Way's center lay thousands of light-years away from us, hidden in Sagittarius. A different kind of light soon provided a clearer direction. During the early 1930s, Carl Jansky was working for Bell Telephone Laboratories in New Jersey. His assignment was practical. Bell wanted to know what kinds of natural radio interference might disturb transatlantic telephone communication. Jansky built a rotating antenna about 30 meters across. It stood on wheels taken from a Model T Ford and could turn through a full circle, allowing him to identify the direction of incoming radio noise. Among the crackles from thunderstorms, he found a steady hiss that returned every 23 hours and 56 minutes. That period matched a sidereal day, the time Earth takes to rotate once relative to the distant stars. The source was therefore beyond Earth. Its strongest signal came from Sagittarius. In 1933, Jansky announced that radio waves were arriving from the central Milky Way. Radio wavelengths can pass through dust that blocks visible light. Their longer waves interact less strongly with the tiny grains spread through the galactic disk. The hidden center had begun to reveal itself without becoming visible to the human eye. 4 decades later, radio instruments narrowed the source further. In February 1974, Bruce Balick and Robert Brown used a radio interferometer at the National Radio Astronomy Observatory in Greenbank, West Virginia. An interferometer combines signals from separated antennas so they work like parts of one much larger telescope. Their observations revealed an extremely compact radio source at the heart of the broader Sagittarius A region. That source later became known as Sagittarius A star. The star symbol in its name marks it as an especially important and energetic radio source. Sagittarius A star remained invisible in ordinary light, yet its position could now be measured with great precision. Infrared astronomy added another layer. Infrared wavelengths pass through much of the intervening dust, allowing observatories in Hawaii and Chile to watch stars moving through the innermost part of the galaxy. Over years of observation, those stars traced curved paths around a point that appeared empty. Their motion showed that millions of times the sun's mass had been packed into an extraordinarily small region. The evidence pointed toward a supermassive black hole. In April 2017, 8 radio observatories spread across Earth observed Sagittarius A star together. This worldwide network was called the Event Horizon Telescope. It recorded radio waves with a wavelength of 1.3 millimeters. Atomic clocks kept the observatories synchronized closely enough for their data to be combined later. 5 years of calibration, reconstruction, and comparison followed. On May 12, 2022, the first Event Horizon scale image of Sagittarius A star was released. The glowing ring in that image was reconstructed from radio measurements. It was not a photograph made with visible light. The structure spans only about 50 microarcseconds across the sky. A microarcsecond is 1/millionth of 1 arcsecond, and 1 arcsecond is only 1/3600th of a degree. Humanity had located, measured, and imaged a destination that remained completely unreachable. By then, a spacecraft could be given a direction, but its launch point was already moving across that direction at more than 200 kilometers every second. A spacecraft aimed toward Sagittarius would begin its journey from a platform already moving through several overlapping orbits. Earth circles the Sun at nearly 30 kilometers per second. The Sun, carrying Earth and the rest of the solar system with it, moves around the Milky Way at a little more than 200 kilometers per second. That galactic motion is more than 7 times faster than Earth's orbital speed around the Sun. The solar system lies in the Orion Spur, a smaller branch of the Milky Way positioned between the larger Sagittarius and Perseus spiral arms. From there, the Sun follows a broad path around the galactic center, roughly 26,000 light-years away. One complete circuit takes approximately 230 million years. Dinosaurs appeared during the solar system's previous galactic year. The earliest dinosaurs lived about 230 million years ago, close to the time required for the Sun to travel once around the Milky Way. Since the Sun formed about 4.6 billion years ago, it has completed only around 20 galactic orbits. Every rocket launched from Earth inherits this motion automatically, A spacecraft on a launch pad is already rotating with Earth. It is also traveling around the Sun. Beyond that, it shares the Sun's movement through the rotating galactic disk. Rocket engines can add velocity or change its direction, but they do not erase the motion the spacecraft had before launch. This matters because the galactic center is not sitting directly ahead of a stationary Earth. The solar system is sweeping sideways around it. A ship pointed visually towards Sagittarius would still carry more than 200 kilometers per second of sideways galactic velocity. Once its engines stop firing, that inherited motion would continue shaping its path. The physical idea behind this is called angular momentum. Angular momentum describes the motion of an object traveling around a center. An orbiting object has forward motion that prevents gravity from pulling it directly inward. Earth is continually falling toward the Sun, but its sideways speed carries it forward fast enough that the surface of the Sun keeps curving away beneath its path. The result is an orbit rather than a collision. The same principle applies on a vastly larger scale to the Sun and the Milky Way. Gravity from the galaxy's distributed mass pulls the solar system inward. Its sideways velocity carries it around the center. A spacecraft leaving Earth begins with that same balance. Traveling deeply inward means changing the balance by reducing or redirecting some of its galactic motion. Aiming the nose of the spacecraft toward the center accomplishes very little by itself. The engines must produce a large change in velocity. Spaceflight engineers call that change delta V. The term means the total amount by which a spacecraft can alter its speed or direction during a mission. Reaching orbit around Earth requires one delta V budget. Escaping the Sun requires another. Changing from the Sun's galactic orbit to a path that carries a spacecraft thousands of light years inward requires a much larger and more complicated maneuver. Earth orbit is the first step. A spacecraft must accelerate to roughly 7.8 kilometers per second to remain in low Earth orbit. Escaping Earth completely from the surface requires a speed near 11.2 kilometers per second. Although real launches reach that state through staged acceleration, rather than one instantaneous push. Leaving the Sun presents a different problem. At Earth's distance, the Sun's escape speed is about 42 kilometers per second. Earth already supplies nearly 30 kilometers per second of orbital motion, so spacecraft can use the planet's movement, rocket thrust, and gravity assists from other worlds to gain the remaining energy. Voyager 1 used close encounters with Jupiter in 1979 and Saturn in 1980 to reshape its solar orbit and place it on an escape path. A galactic center mission would need to go far beyond that achievement. Escaping the Sun removes the spacecraft from the solar system's local gravitational control. It does not remove the velocity inherited from the Sun's orbit around the Milky Way. The craft would still be traveling through the galaxy at hundreds of kilometers per second, following a path influenced by the same galactic gravity acting on nearby stars. A direct inward journey would require propulsion to reshape that orbit over an immense distance. The ship might brake against its inherited sideways motion before accelerating inward. Another design might combine both changes gradually, bending the trajectory into a long curve through the galactic disk. Either approach requires energy far beyond the amount needed to leave Earth or escape the Sun. The journey, therefore, begins with a demanding correction before the spacecraft has closed any meaningful fraction of the 26,000 light-year distance. Humanity has already built machines capable of escaping the solar system. Their speeds reveal how far current propulsion remains from changing a galactic orbit on a useful timescale. The machines that have reached the highest speeds in human history achieved them under very specific conditions. Parker Solar Probe holds the record. NASA launched it from Cape Canaveral on August 12, 2018, sending it into a series of tightening orbits around the Sun. During its closest solar passes, Parker reaches approximately 430,000 miles per hour, or about 690,000 kilometers per hour. At that speed, it could cross the width of the United States in less than 30 seconds. Its closest approaches carry it to roughly 3.8 million miles above the Sun's visible surface. Mercury, the innermost planet, remains about 22 million miles from the Sun at its closest point. Parker travels far inside Mercury's orbit, through the Sun's outer atmosphere, where temperatures around the spacecraft can rise above 1,000 degrees Celsius. The probe survives behind a carbon composite heat shield, measuring about 11.5 centimeters thick. Its record velocity comes largely from the Sun's gravity. Parker follows a long, stretched orbit called an ellipse. As it falls inward, gravitational energy becomes motion, causing the spacecraft to accelerate. The fastest moment occurs near perihelion, the point in its orbit closest to the Sun. After passing perihelion, Parker begins climbing outward through the Sun's gravitational field and gradually loses speed. The same pattern occurs with a ball thrown upward on Earth. The ball slows as it rises because gravity pulls against its motion. Parker experiences this process on a solar scale. Its record therefore describes the fastest portion of an orbit. It does not represent a cruise speed the probe could carry towards Sagittarius A star. Parker also used repeated flybys of Venus to reshape its orbit. Each encounter removed a small amount of the spacecraft's orbital energy, allowing the next solar pass to come closer to the Sun. The planet's gravity helped Parker fall deeper and move faster during perihelion. A spacecraft traveling outward toward another star would need a different trajectory. Once it climbed away from the Sun, much of the speed gained during the fall would disappear. Voyager 1 provides a cleaner example of a spacecraft genuinely departing. It launched on September 5, 1977, aboard a Titan rocket from Cape Canaveral. The spacecraft reached Jupiter in March 1979 and Saturn in November 1980. Each planet supplied a gravity assist. During a gravity assist, a spacecraft passes through a moving planet's gravitational field and exchanges a tiny amount of momentum with it. The planet's motion around the Sun can bend the spacecraft's path and increase its solar escape speed without requiring the craft to burn an equal amount of fuel. Saturn's final gravitational push placed Voyager 1 on a permanent outward trajectory. Today, it travels relative to the Sun at approximately 17 kilometers per second. That equals about 61,000 kilometers per hour. Every year, Voyager increases its distance from the Sun by roughly 3.5 astronomical units. 1 astronomical unit is the average distance between Earth and the Sun, about 150 million kilometers. Voyager therefore covers more than 500 million kilometers of outward distance each year. Human standards make that motion seem extraordinary. A signal from Earth now requires nearly a full day to reach the spacecraft. Voyager crossed the heliopause in August 2012, entering the region where the surrounding plasma comes mainly from interstellar space rather than the solar wind. It has traveled farther from Earth than any other human-built object. yet 17 kilometers per second remains extremely slow beside the scale of the Milky Way. 1 light year contains about 9.5 trillion kilometers. Voyager covers slightly more than 500 million kilometers in 1 year. At that pace, traveling 26,000 light years would require approximately 458 million years. The calculation assumes a perfectly direct route and a constant speed. It ignores the effort required to change the ship's galactic orbit. It also leaves out acceleration at departure and braking near the center. During 458 million years, the solar system would complete nearly 2 full circuits around the Milky Way. Continents would move across Earth. Entire groups of organisms would appear and disappear from the fossil record. Voyager's achievement remains remarkable because a machine built in the 1970s continues moving and communicating in interstellar space. Its speed also reveals the boundary between present spacecraft and the vehicle this journey would require. Crossing the galaxy on a useful timescale demands propulsion systems that remain experimental, theoretical, or far beyond anything yet constructed. The first step above chemical rockets is electric propulsion. An electric thruster uses electrical energy to accelerate charged particles out of the back of a spacecraft. The particles may leave the engine at tens of kilometers per second, far faster than the exhaust from a chemical rocket. The thrust itself remains extremely gentle. NASA's Dawn spacecraft used ion engines that pushed with a force comparable to the weight of a sheet of paper resting on a hand. That small force continued for months at a time. Across its mission to the asteroid Vesta and the dwarf planet Ceres, Dawn accumulated about 11 kilometers per second of velocity change. A chemical rocket can produce enormous thrust for several minutes. An ion engine can continue producing a small push for years as long as electricity and propellant remain available. That makes electric propulsion useful for gradual journeys through the solar system. A nuclear reactor could provide far more electricity than distant solar panels, allowing larger and more powerful electric engines to operate far from the sun. The spacecraft would still accelerate slowly. Reaching even 1% of light speed would require sustained operation, a large power source, and an engine capable of surviving far longer than any electric thruster has operated. A more forceful concept was studied during the early years of the space age. Project Orion began in 1958 under the United States Advanced Research Projects Agency and later continued with support from the Air Force. Its designers proposed dropping small nuclear explosive devices behind a spacecraft. Each explosion would strike a thick metal pusher plate. Shock absorbers between the plate and the vehicle would soften the impacts into a series of powerful pushes. Tests using ordinary explosives showed that a pusher plate could survive repeated blasts. A full Orion spacecraft was never built. Atmospheric nuclear test restrictions, radioactive fallout, political concerns, and the enormous scale of the vehicle ended serious development during the 1960s. The project remains important because it treated nuclear pulse propulsion as an engineering study rather than a fictional idea. Its proposed vehicles could have carried thousands of metric tons, making Orion one of the few advanced concepts designed around genuinely large payloads. Fusion propulsion offers a cleaner version of the same broad ambition. Fusion joins light atomic nuclei and releases energy from a small loss of mass. The Sun performs this process naturally by combining hydrogen into helium under immense pressure and temperature. a fusion spacecraft would need to create controlled reactions, direct the released energy into an exhaust stream, and protect the vehicle from heat and neutron radiation. Project Daedalus, designed by the British Interplanetary Society between 1973 and 1978, proposed using tiny fusion pellets inside an uncrewed interstellar probe. Electron beams would ignite the pellets one after another. The expanding plasma would be directed backward by magnetic fields. The study imagined reaching about 12% of light speed during a mission to Barnard's star. Daedalus remained a paper design. Humanity has produced controlled fusion reactions in laboratories, but no fusion power plant currently supplies electricity to a grid, and no operational fusion rocket has flown. Antimatter offers even greater energy density. Every particle of ordinary matter has an antimatter counterpart with the same mass and opposite electrical charge. When matter and antimatter meet, their mass can be converted into other particles and radiation. This makes annihilation one of the most energy-rich processes known to physics. Particle accelerators can manufacture antiprotons and other forms of antimatter. The quantities are microscopic. Production consumes far more energy than the antimatter later releases, and storage requires electromagnetic traps that prevent contact with ordinary material. An antimatter engine would also need to convert a violent mixture of radiation and fast particles into controlled thrust. Its fuel system could not tolerate a containment failure. NASA's Innovative Advanced Concepts program has supported early studies involving fusion, directed energy, antimatter-assisted propulsion, and streams of fast pellets. These studies explore physical possibilities and identify the engineering barriers. They are several steps removed from vehicles ready for construction. The highest proposed speeds usually appear when the spacecraft leaves its engine behind. A powerful laser array could focus light onto a reflective sail. Photons carry momentum, so the beam would push the sail without requiring the craft to carry a reactor or most of its propellant. Breakthrough Starshot, announced in 2016, studies this approach for extremely small spacecraft. The concept uses a gram-scale electronic probe attached to a lightweight sail. A laser array on or near Earth would illuminate it for several minutes and attempt to accelerate it to roughly 20% of light speed. That velocity could carry a tiny probe to Alpha Centauri in a little more than 20 years. The same craft would require about 130,000 years to reach the center of the Milky Way. A person, a large telescope, or a self-repairing laboratory would increase the mass enormously. The laser power would need to increase with it. The fastest idea on this ladder works partly because the proposed traveler weighs about as much as a small coin and carries only a thin collection of instruments. Speed alone, therefore, gives an incomplete picture. Once a spacecraft has been accelerated, that motion contains an immense amount of energy that must remain controlled throughout the journey and somehow be removed when the destination finally arrives. A spacecraft moving at 20% of light speed carries more than velocity. Its motion stores an enormous amount of energy. Physicists call this kinetic energy, meaning the energy an object possesses because it is moving. A slow-moving object gains kinetic energy when its mass increases or when its speed rises. Near the speed of light, the energy requirement grows even more sharply because relativity begins to matter. Consider an imaginary spacecraft with a total mass of 1,000 metric tons. That equals 1 million kilograms, a little more than twice the mass of the International Space Station. This is only an example used to make the calculation concrete. It is not a proposed design for a galactic mission. At 10% of light speed, the craft would travel at almost 30,000 kilometers per second. Its kinetic energy would be approximately 4.53 times 10 to the 20th joules. Written in ordinary spoken terms, that is about 453 billion joules stored in the ship's motion. At 20% of light speed, the same craft would move at almost 60,000 kilometers per second. Its kinetic energy would rise to about 1.85 times 10 to the 21st joules. Doubling the speed would therefore increase the energy by a little more than 4 times. Those figures describe the motion of the spacecraft alone. They do not include the energy lost inside the engine. They exclude the fuel tanks, shielding, radiators, living space, repair equipment, and power systems that would make the mission possible. The energy source would need to provide far more than the final kinetic energy, because every real engine wastes part of its input. Carrying the energy supply aboard the spacecraft creates an additional problem. A rocket moves by throwing mass backward. The faster the exhaust leaves, the more efficiently the rocket can change its own velocity. Chemical engines eject hot gas at only a few kilometers per second. That is useful for launching from Earth and traveling between nearby planets. A mission seeking tens of thousands of kilometers per second requires a much higher exhaust velocity. The relationship between propellant, exhaust speed, and spacecraft velocity is described by the ideal rocket equation. Its most important consequence is simple. Adding propellant increases the spacecraft's starting mass. Accelerating that additional mass requires still more propellant. The extra propellant must also be accelerated, creating a rapidly growing cycle. Suppose a spacecraft needs one large velocity change to accelerate toward the galactic center. It also needs another large velocity change to slow down near Sagittarius A star. The fuel reserved for braking must be carried throughout the entire outward journey. The first stage engines must accelerate the ship, its payload, and the propellant that will remain unused for thousands of years. Higher exhaust velocity can reduce this penalty. Fusion, antimatter, and beamed propulsion are attractive partly because they could produce far faster exhaust or leave part of the energy source behind. None removes the need to manage energy inside the vehicle. A nuclear electric spacecraft would begin with a reactor producing heat. Only part of that heat could be converted into electricity. The electrical system would then power the engines, computers, pumps, sensors, and life support equipment. Unused heat would accumulate unless the spacecraft released it. On Earth, machines can pass heat into air or cooling water. Space provides no surrounding material to carry it away. A spacecraft must radiate heat as infrared light from large external panels. These radiators need enough surface area to remain cool while the power system operates. A more powerful engine produces more waste heat and requires larger radiators. Those panels add mass, and their thin surfaces remain exposed to dust impacts throughout the journey. The same difficulty returns at the destination. A spacecraft arriving at 20% of light speed still carries about 1.85 times 10 to the 21st joules of kinetic energy for every 1,000 metric tons of mass. Entering a controlled orbit requires removing almost all of that motion relative to the galactic center. Engines could turn the ship around and fire in the opposite direction. A destination-based laser might push against a sail. A magnetic system could interact with surrounding charged particles over a much longer distance. Every option requires equipment, time, and a dependable way to redirect or release the ship's energy. Without braking, the spacecraft would cross 1 light-year in about 5 years. It could pass through the entire central region before completing a detailed survey. The journey would become a flyby, lasting only a tiny fraction of the time spent reaching it. Speed therefore changes the mission long before arrival. The energy stored in the ship is also present in every collision with material lying ahead. At 20% of light speed, even a microscopic grain drifting quietly between the stars can strike with the concentrated force of an explosion. The material ahead of the spacecraft would be extremely thin. It would still extend across 26,000 light-years of travel. The space between stars contains hydrogen, helium, free electrons, cosmic rays, and microscopic grains of solid material. Much of the gas exists at densities near 1 atom per cubic centimeter, although the exact value changes from one region of the galaxy to another. A cubic centimeter is about the size of a small sugar cube. Earth's atmosphere at sea level contains roughly 10 billion particles inside that same volume. Interstellar space is therefore an extraordinary vacuum by ordinary standards. A fast spacecraft experiences that vacuum as a continuous stream of impacts. The danger comes from relative motion. A hydrogen atom drifting quietly through the galaxy may carry very little energy from its own point of view. To a ship moving at 20% of light speed, the atom approaches at almost 60,000 kilometers per second. Each collision transfers energy into the surface of the vehicle. Individual atoms would behave less like a gentle gas and more like high-energy radiation. They could strip electrons from materials, damage computer memory, weaken chemical bonds, and gradually alter the structure of exposed shielding. Charged particles can sometimes be redirected with electric or magnetic fields. A magnetic field bends the path of a moving charged particle by applying a force across its direction of travel. The same basic process helps Earth's magnetic field deflect part of the solar wind. Neutral hydrogen atoms carry no net electrical charge. A magnetic shield would have little direct effect until those atoms were ionized, meaning one or more electrons had been removed. Dust presents a harder problem. Interstellar grains can contain silicate minerals similar to rocky material on Earth. Others contain carbon compounds or layers of frozen material. NASA's Stardust spacecraft carried a collector made from aerogel, an extremely light material, filled mostly with empty space. During the mission, the collector captured tiny particles moving through the solar system. Several candidates may have arrived from interstellar space, although identifying their origin required years of careful laboratory analysis. Those grains were microscopic. At ordinary spacecraft velocities, a small grain can pit a surface or damage delicate equipment. At relativistic speed, the same mass delivers far more energy. Consider a dust grain weighing 1 microgram. 1 microgram is 1/1,000,000th of a gram, far lighter than a visible grain of table salt. At 10% of light speed, its impact energy relative to the spacecraft would be approximately 453 kilojoules. That is comparable to the kinetic energy carried by a small car moving at highway speed, concentrated into an object too small to see easily. At 20% of light speed, the energy rises to about 1.85 megajoules. The grain would vaporize on contact. Part of the spacecraft's surface would also flash into hot gas and plasma around the impact point. Even when the crater remained small, repeated strikes could gradually remove shielding or damage instruments buried beneath it. A larger grain would be far more destructive. Breakthrough Starshot studies this problem because its proposed gram-scale probes might travel near 20% of light speed. The intended journey to Alpha Centauri covers a little more than 4 light-years. A galactic center mission would cross more than 6,000 times that distance, multiplying the opportunities for impacts and gradual erosion. The simplest protection would be a thick shield placed at the front of the vehicle. Several layers could spread the energy from an impact before it reached the main spacecraft. Outer sections might be designed for replacement as they wore away. Materials rich in hydrogen could also help reduce some forms of radiation exposure. Mass remains the central penalty. Every kilogram of shielding must be accelerated to cruise speed and slowed again near the destination. A thicker shield increases the propulsion energy, which may require a larger power system and more heat control equipment. Some designs place material ahead of the spacecraft. A cloud of fine particles released into the flight path could strike incoming dust first, breaking larger grains into smaller fragments before they reach the hull. The craft might also carry lasers or radar systems to search for larger objects. Detection becomes difficult at relativistic speed because the distance closes rapidly. At 20% of light speed, the ship travels almost 60 million kilometers every second. A hazard detected 1 million kilometers ahead would be reached in less than 2/100ths of a second. Protection therefore depends heavily on passive shielding and systems that respond automatically. The forward surface would experience this environment throughout the entire crossing. Its layers would erode. Sensors would lose accuracy. Microscopic damage would accumulate inside materials that still appeared solid from the outside. A shield designed to survive several decades would cover almost none of a 130,000-year journey. The spacecraft would need to inspect the damage, manufacture replacement material, and rebuild its own protection repeatedly while moving through the galaxy. That rebuilding process would have to continue far beyond the lifetime of any spacecraft humans have ever made. Voyager 1 offers the strongest real example of long-term survival in deep space. It launched on September 5, 1977, with computers holding less memory than a modern digital photograph. Nearly half a century later, it has continued returning measurements from beyond the heliopause. That longevity came from careful engineering, backup systems, and repeated intervention from teams on Earth. Voyager carries 3 radioisotope thermoelectric generators. These devices use heat from the natural decay of plutonium-238 to produce electricity. At launch, the generators supplied about 470 watts. Their output has fallen steadily as the plutonium decays and the electrical components age. The spacecraft loses roughly 4 watts of available power each year. NASA has responded by switching off heaters and scientific instruments one at a time. The cameras stopped operating after Voyager's final planetary images in 1990. More recently, engineers have continued choosing which remaining instruments can stay active without draining the shrinking power supply. Voyager's survival across decades is extraordinary. A craft traveling at 20% of light speed would still need around 130,000 years to reach the galactic center. That interval is roughly 2,600 times longer than Voyager's first 50 years. No engineer could reasonably expect one original set of bearings, seals, processors, sensors, or reactor components to operate untouched for that duration. Metal slowly becomes brittle under radiation. Lubricants break down. Electronic memory develops errors when energetic particles pass through circuits. Thin radiators collect impact damage while repeatedly expanding and contracting as their temperature changes. The spacecraft would therefore be designed around replacement rather than endurance alone. Robotic systems would inspect the hull and compare new measurements with stored reference data. Damaged parts would be removed and remade from material carried aboard or gathered during the journey. A manufacturing bay might melt metals, purify them, and shape them into new structural pieces. More delicate equipment would require the ability to produce wiring, computer components, optical surfaces, and precision sensors. Repairing the spacecraft once would not be enough. The machines performing the work would also wear out. A maintenance robot would need replacement joints and fresh cameras. The equipment building those parts would need recalibration. Backup factories would remain isolated from the main system, so that one accident, software failure, or contamination event could not disable every means of recovery. Raw material would become as important as fuel. The craft might carry blocks of aluminium, carbon-rich compounds, silicon, copper, and other elements selected for repeated manufacturing cycles. Some material could be recycled from failed components. Every recycling process would lose a small amount through contamination, erosion, or incomplete recovery. Over 130,000 years, even tiny losses could accumulate. Information would require the same renewal. Radiation can flip individual bits inside computer memory, changing a 0 into a 1. Error-correcting systems detect these changes by storing extra information and comparing multiple copies. Across geological timescales, the archives would need to be checked, repaired, and copied onto fresh hardware repeatedly. Navigation tables, engine designs, medical knowledge, and manufacturing instructions would pass through thousands of replacement cycles. The meaning of those records would also need protection. A diagram becomes useless when future systems no longer understand its symbols or assumptions. The craft would need permanent translation layers, test examples, and physical reference standards showing what its measurements meant. Mission instructions would require similar care. A self-modifying system may adapt successfully for thousands of years, while gradually drifting away from its original purpose. Safeguards would need to preserve the destination, the arrival plan, and the reason the journey began. By the time the spacecraft reached Sagittarius A star, most of its original hardware might be gone. Its identity would survive through preserved information and continuous function, rather than through the material launched from Earth. That continuity could no longer depend on human instructions arriving at the right moment. As the distance increased, even the fastest message from Earth would take years, then centuries to reach the ship. During the early part of the journey, messages would still move quickly enough for mission control to remain useful. Radio signals travel at the speed of light, about 300,000 kilometers per second. From Earth to the Moon, the delay is only about 1.3 seconds. Mars is much less convenient because its distance changes as both planets orbit the Sun. A one-way transmission may take a little more than 3 minutes when Mars is nearby, and more than 20 minutes when it is far away. Voyager 1 already shows how distance changes routine operations. A command sent from Earth takes nearly a full day to reach the spacecraft. Engineers must then wait almost as long for confirmation that the instruction worked. A simple exchange stretches across close to 2 days. Those delays remain small beside an interstellar journey. Once the ship is 1 light year from Earth, every message requires 1 year to arrive. A request for help followed by the earliest possible response would take at least 2 years. The fault that triggered the request might already have been repaired, transformed into a larger failure, or rendered irrelevant by the time instructions returned. At 10 light years, a complete exchange takes 20 years. The engineers who receive a reply may be different people from those who sent the original message. After 1,000 light years, a transmission sent toward Earth arrives 1,000 years later. Any response requires another 1,000 years to reach the ship. Civilizations have risen, changed languages, and disappeared within shorter periods. Near Sagittarius A star, a message sent home would need about 26,000 years to cross the galaxy. A reply could not return for roughly 52,000 years. More powerful transmitters cannot shorten that delay. They can only make the signal easier to detect. Radio waves spread outward as they travel, distributing their energy across an expanding area. Doubling the distance reduces the amount of signal reaching a receiving antenna to roughly 1/4. At galactic distances, even a powerful broadcast becomes extraordinarily faint. A laser can concentrate energy into a much narrower beam. NASA has already tested this approach through the Deep Space Optical Communications experiment carried aboard the Psyche spacecraft. In December 2024, the system transmitted data from approximately 307 million miles away. That distance is greater than the widest separation between Earth and Mars. The experiment showed that carefully aimed infrared light can carry useful information across hundreds of millions of miles. The center of the Milky Way lies roughly 500 trillion times farther away than that demonstration distance. A beam traveling across the galaxy would need exceptional pointing accuracy. The spacecraft could not aim at Earth's current position. Light would spend 26,000 years in transit, while the Sun continued moving around the Milky Way. At a little more than 200 kilometers per second, the solar system would travel thousands of light years along its galactic orbit during the signal's journey. The transmitter would have to predict where the receiving system would be when the beam arrived. Earth might no longer host the antenna that had been planned in 2026. A future civilization could build enormous receiving arrays elsewhere in the solar system, perhaps around the Moon or in orbit around the Sun. The ship could also send the same data repeatedly over centuries, increasing the chance that some version reached a working receiver. Communication would still become a record sent across history. Earth could transmit scientific discoveries, cultural archives, and updates about later missions. The ship would receive them long after the events had occurred. Its own reports would describe conditions from a place Earth would not learn about until another 26,000 years had passed. Mission control would gradually lose its practical role. The spacecraft would choose routes, manage repairs, and respond to hazards without waiting for permission. To do that, it would need more than a map prepared before launch. Every useful landmark in the Milky Way would continue moving while the ship traveled toward it. The spacecraft would begin with the most precise stellar map humanity has ever produced. The European Space Agency launched the Gaia Observatory on December 19, 2013. Its main observing campaign began in July 2014 and continued until January 15, 2025. During that period, Gaia recorded more than 3 trillion individual observations of approximately 2 billion stars and other objects. It measured where they appeared in the sky, how bright they were, and how their light changed over time. For many stars, Gaia also estimated temperature, chemical composition, distance, and motion. The technique behind this work is called astrometry. Astrometry is the precise measurement of positions and movement across the sky. Gaia repeatedly observed the same stars as Earth traveled around the Sun. Nearby stars seemed to shift slightly against more distant backgrounds. That tiny apparent movement is called parallax. The effect resembles holding up one finger and viewing it first through one eye, then the other. The finger appears to move because the viewing position has changed. A larger parallax means a star is closer. Even Gaia's enormous catalogue contains only about 1% of the Milky Way's estimated stellar population. Dust hides many stars in the galactic disk. Others are too faint, too distant, or too crowded together for precise measurement. The catalogue would still give the departing ship a detailed map of its local surroundings and many distant reference points. A recorded position alone would quickly become outdated. Stars move. Proper motion describes a star's apparent movement sideways across the sky. Radial velocity measures how quickly it approaches or recedes along the observer's line of sight. Combining those measurements gives a 3-dimensional estimate of velocity. A star located 10 light-years away in 2026 may occupy a noticeably different position thousands of years later. Small uncertainties also grow with time. An error of 1 kilometer per second in a velocity estimate becomes a positional error of more than 3 light-years after 1 million years. Gravity adds further changes. Binary stars orbit one another. Passing stars alter nearby trajectories slightly. Large clouds and the overall gravitational field of the Milky Way bend paths over long periods. The spacecraft would therefore treat Gaia's map as a starting model, rather than a permanent chart. Some of its most useful landmarks would be pulsars. A pulsar is the collapsed core left behind after a massive star explodes. Many contain more mass than the Sun compressed into a sphere only about 20 kilometers wide. They rotate rapidly and sweep beams of radiation through space. When a beam crosses the spacecraft's position, the instrument detects a pulse. Millisecond pulsars complete hundreds of rotations every second. Their timing can remain stable enough to function like natural clocks spread across the galaxy. In 2017, NASA tested this idea aboard the International Space Station. The experiment was called Station Explorer for X-ray timing and navigation technology, or sextant. It used an X-ray telescope to observe pulsars and calculate the station's position without relying entirely on signals from Earth. The demonstration showed that pulsar navigation could work autonomously in real time. A galactic spacecraft could compare the arrival times of pulses from several known sources. Slight differences between the expected and observed timing would reveal changes in its position. Pulsars would provide broad galactic reference points, while nearby stars and gas clouds would refine the local route. The ship would also monitor its own acceleration. Every engine firing, dust impact, and gravitational encounter could shift the trajectory slightly. Repeated observations would allow its computers to compare the predicted path with the path actually traveled. New stars would enter view as the spacecraft moved inward. old reference objects would drift behind it. Some pulsars would slow down, suffer sudden changes in rotation, or become too faint to remain useful. Fresh measurements would replace aging predictions. The spacecraft would spend the entire journey rebuilding its understanding of where it was. Its map would remain alive because the galaxy itself remained in motion. Once those moving landmarks were placed around the ship, the straight line toward Sagittarius opened into a route through the Orion Spur and the larger spiral structures beyond it. The first part of the route would pass through the solar system's own galactic neighborhood. The Sun lies inside the Orion Spur, sometimes called the Orion Arm. This is a smaller branch of the Milky Way positioned between two larger structures, the Sagittarius Arm toward the galactic center and the Perseus Arm farther outward. Our location is roughly 26,000 light-years from Sagittarius A star and about halfway between the galaxy's center and its visible outer edge. A spacecraft heading inward would gradually leave the stars and clouds associated with the Orion Spur. Depending on its exact trajectory, it would move toward the Sagittarius Carina Arm and the denser regions of the inner galactic disk. These names can make the arms sound like solid objects with sharp edges. Their boundaries are broad and irregular. A spiral arm may be hundreds or thousands of light-years wide, containing areas of dense gas separated by much emptier regions. Stars pass into and out of these patterns as they orbit the galaxy. The arms remain recognizable because gas becomes compressed within them. Denser gas can cool and collapse under its own gravity. That collapse produces new stars, often in groups hidden inside the clouds where they formed. Young, massive stars then heat the surrounding material with ultraviolet radiation and powerful stellar winds. Their short lives may end in supernova explosions only a few million years later. This makes spiral arms especially rich in glowing nebulae, dark dust clouds, and young star clusters. The Orion Nebula provides a nearby example within our own spur. It lies about 1,300 light-years from Earth and contains stars forming inside a cloud of hydrogen and dust. The Sagittarius Arm contains larger star-forming regions farther toward the center, including the Eagle Nebula and the Lagoon Nebula. Many of these structures are difficult to see in visible light because dust absorbs the light from the stars developing inside them. Infrared telescopes reveal more of the hidden structure. NASA launched the Wide Field Infrared Survey Explorer, known as WISE, in December 2009. Its detectors map the entire sky at infrared wavelengths. Warm dust and deeply embedded young stars appear clearly in infrared light, allowing astronomers to identify clusters concealed inside the Milky Way's arms. WISE observations help trace nearly 100 young embedded clusters across the Perseus, Sagittarius Carina, and outer arms. These clusters are useful markers because their stars have not yet had enough time to drift far from the gas where they formed. Even with infrared surveys, the Milky Way remains difficult to map. Astronomers observe it from inside its thin disk. Dust blocks portions of the far side, while overlapping stars and clouds make distance measurements difficult. A galaxy viewed from above would display its structure clearly. From Earth, the same arms appear layered along our line of sight. The spacecraft would eventually gain a changing perspective unavailable from the solar system. As it traveled inward, nearby clouds would shift behind it, and distant structures would separate into clearer layers. Its instruments could update the shape of the arms using star positions, radio emissions from hydrogen, and infrared observations of dust. The shortest route towards Sagittarius A star would not automatically be the safest. A straight path might intersect a dense molecular cloud containing far more gas and dust than the surrounding interstellar medium. It could also cross an active region filled with young massive stars, strong ultraviolet radiation, and recent supernova remnants. A curved route could avoid the densest structures while adding hundreds of light years to the journey. At 20% of light speed, an additional 100 light years would add about 500 years of travel. That delay could still be worthwhile if it reduced damage to the forward shield or lowered radiation exposure. The Milky Way would therefore become a navigable landscape with safer corridors and regions worth avoiding. Each part of that landscape would also carry its own physical conditions. Gas density could change by enormous amounts from one cloud to the next, while temperature, magnetic fields, and cosmic radiation altered the environment surrounding the ship. A spacecraft leaving one spiral region for another would encounter changing forms of interstellar matter. Some stretches would contain warm neutral gas, mostly hydrogen atoms that still hold their electrons. Other regions would be filled with ionized plasma, where heat or radiation has stripped electrons away from atoms. Cold clouds would hold more tightly packed gas and dust, while enormous cavities created by ancient stellar explosions could contain extremely thin material heated to millions of degrees. The solar system already sits inside one of those cavities. It is called the local bubble. This region extends for several hundred light years and was probably carved by multiple supernova explosions during the past 10 to 20 million years. The hot gas inside it is much thinner than the air in any laboratory vacuum chamber. Within the local bubble, the Sun is passing through a smaller patch called the local interstellar cloud. Voyager 1 and Voyager 2 entered interstellar space in 2012 and 2018. Their instruments found that the surrounding plasma does not have one perfectly constant density. Voyager 1 measured changes in the number of free electrons as it traveled outward. Plasma waves allowed scientists to estimate that density because the natural vibration frequency of plasma depends on how many charged particles it contains. Those measurements showed gradual changes over distances of several astronomical units. 1 astronomical unit is the average distance between Earth and the Sun. Conditions already vary across our immediate galactic neighborhood. Farther inward, the differences would become much larger. A warm, neutral region might contain a fraction of 1 atom per cubic centimeter. A dense molecular cloud can contain thousands or millions of particles inside the same volume. Molecular clouds are cold enough for hydrogen atoms to join into pairs, forming hydrogen molecules. Temperatures in their darkest interiors may fall to around 10 degrees above absolute zero. That is close to minus 263 degrees Celsius. A million-degree plasma sounds far more dangerous. Temperature describes the average energy carried by each particle. It does not tell us how many particles are present. A human placed inside extremely thin million-degree gas would encounter very few collisions. The gas would transfer heat slowly because its particles are spread so widely apart. A cold molecular cloud could strike the spacecraft with far more total material. At relativistic speed, its low temperature would offer no protection. The gas and dust would approach the ship at the vehicle's full travel velocity. Magnetic fields add structure to these regions. The Milky Way contains weak fields extending across clouds and spiral arms. Charged particles spiral around magnetic field lines as they move. This affects how cosmic rays travel through the galaxy and which directions they approach from. Cosmic rays are fast atomic nuclei and electrons produced by sources such as supernova remnants and pulsars. Some carry energies far beyond those created in ordinary nuclear reactions. The inner Milky Way contains more supernova remnants, neutron stars, molecular clouds, and long magnetic filaments than the quieter region near the Sun. A supernova blast can drive a shockwave through surrounding gas for tens of thousands of years. The expanding shell compresses material ahead of it and leaves a hot, thin cavity behind. By the time the spacecraft reaches the location, the original star may have become a neutron star or black hole, while the disturbed region continues spreading through space. The ship would need instruments looking far ahead. Radio observations could measure neutral hydrogen. Infrared sensors could detect warm dust hidden inside clouds. X-ray instruments could reveal hot plasma and energetic remnants. The route planner would compare those observations with expected conditions and adjust course before entering a dangerous region. At 20% of light speed, 1 light year passes in about 5 years. A cloud detected several light years ahead may still leave time for a gradual course change. The launch map could never predict the entire journey accurately. Across 130,000 years, clouds collapse into stars, shock waves expand, and magnetic structures shift through the galactic disk. The spacecraft would travel through a sequence of changing environments, each measured again as it approached. Those environments would also continue evolving while the ship crossed the distance toward them. Travel time would therefore determine far more than the arrival date. It would determine which version of the Milky Way remained waiting at the center. A spacecraft moving at 20% of light speed would require about 130,000 years to reach the galactic center. That interval is brief compared with the age of the Milky Way, which formed more than 13 billion years ago. It is still long enough for the route to change in measurable ways. Stars near the Sun move at different speeds and in slightly different directions as they orbit the galaxy. Across 130,000 years, many would shift by several light years from the positions recorded in 2020. The familiar constellations would lose their present shapes. Barnard's star provides a nearby example. It has the largest known proper motion of any star visible from Earth, crossing the sky by about 10 arcseconds each year. An arcsecond is 1/3600th of a degree. That movement appears tiny during a human lifetime. Extended across 130,000 years, it would carry the star across an angular distance greater than a full circle around the sky. Gas clouds would also change. Cold regions could collapse into new stars. Young clusters would push surrounding material outward through radiation and stellar winds. Massive stars born early in the journey might complete their lives before the spacecraft reached the center. The largest stars can survive for only a few million years, while smaller stars remain active for billions or even trillions. At 20% of light speed, the broad Milky Way would remain recognizable. Its disk, central bulge, and major spiral structures would still exist. Individual clouds and clusters along the route could look very different from their launch day maps. Reducing the speed to 10% of light speed doubles the journey to approximately 260,000 years. Small errors in stellar velocity would then grow into larger errors in position. A star whose motion was misjudged by only 1 kilometer per second would end up nearly 1 light-year from its predicted location after that much time. The spacecraft's updated observations would become more useful than the original catalogue carried from Earth. At 1% of light speed, the crossing would last about 2.6 million years. That span is long enough for many massive stars seen in 2026 to explode as supernovae. Their expanding remnants could travel through surrounding gas for tens of thousands of years. New stars would emerge from clouds that had not yet begun collapsing when the spacecraft departed. Some young clusters would disperse as their stars drifted apart under the gravitational pull of the galaxy. The route would pass through a Milky Way whose local details had been repeatedly rewritten. Voyager 1's speed produces a far more extreme result. At approximately 17 kilometers per second, the straight crossing would take about 458 million years. The solar system requires roughly 230 million years to complete one orbit around the galactic center. During a Voyager speed journey, the Sun would travel around the Milky Way almost twice. The spacecraft and the solar system would follow different galactic paths throughout that time. Spiral patterns would shift. Molecular clouds would form and disperse. Generations of massive stars would be born and destroyed, enriching the interstellar medium with oxygen, carbon, iron, and other heavy elements. The destination itself would remain anchored by Sagittarius A star, a black hole containing about 4 million times the Sun's mass can persist across periods far longer than hundreds of millions of years. Its surroundings would be far less stable. The nearby stars would occupy different orbits. Gas flowing toward the center would gather into new clouds and streams. Star clusters visible from Earth in 2026 might disperse, while others formed long after the launch could surround the arriving spacecraft. The chosen speed therefore determines the environment waiting at the end. A fast probe would enter a future version of the galaxy that remained broadly familiar. A slow craft would arrive after traveling through hundreds of millions of years of galactic change. Machines might preserve themselves by replacing parts and renewing their information across those spans. A mission carrying living humans would have to preserve an entire biological and social world. The answer depends on what humanity expects to arrive. The lightest option would be a tiny, uncrewed probe attached to a reflective sail. Breakthrough starshot studies spacecraft weighing only a few grams because very low mass allows a powerful laser beam to produce rapid acceleration. A probe that small could carry miniature cameras, sensors, and a basic communication system. Its shielding would remain thin. Available electrical power would be limited, and the laser used at departure would no longer help once the craft had traveled beyond its beam. A gram-scale vehicle might collect a brief set of measurements near Sagittarius A star. Conducting repairs, manufacturing replacement parts, or operating a large scientific laboratory would require capabilities far beyond anything that can currently fit into such a small mass. A larger autonomous probe could perform a more complete mission. It might carry several telescopes, chemical analyzers, radiation detectors, and robotic equipment able to collect material after arrival. Multiple reactors could provide backup power. Stores of metal, silicon, carbon, and other useful elements would supply manufacturing systems during the journey. Artificial intelligence could manage navigation and repairs without waiting for instructions from Earth. Each addition would make the vehicle harder to accelerate. A probe weighing thousands of metric tons cannot respond to the same laser beam, like a sail weighing a few grams. Greater scientific ability, therefore, produces a slower or far more energy-intensive mission. Biological cargo creates a different design. A seed ship would carry the beginnings of life rather than a living population. Its storage chambers might contain frozen cells, embryos, seeds, microorganisms, or digital genetic records. Human embryos could occupy far less space than adult passengers and would consume no food or oxygen during most of the crossing. Arrival would create the hardest part of the mission. Robotic systems would need to develop the embryos safely, provide medical care, and raise children who had no living parents or established human community. The ship would also need to decide when conditions were safe enough to begin that process. A genetic archive alone could recreate information about humanity without recreating human lives. Cells require suitable wombs, development, education, and years of care before they become independent people. No machine has demonstrated the ability to perform that entire chain. A world ship would carry a functioning society from the beginning. European Space Agency researchers, discussing interstellar travel in 2019, treated artificial gravity, life support, language change, habitability, and sociology as separate engineering problems. A rotating habitat could produce artificial gravity by pushing its occupants toward the outer wall. Farms would need to grow food under artificial light while recycling nutrients from waste. Water vapor, urine, and washing water would pass through purification systems again and again. NASA already develops regenerative life support technology for long missions. Systems aboard the International Space Station recover much of the crew's water and remove carbon dioxide from the cabin air. A galactic journey would demand far greater closure. A loss of even a tiny percentage each year becomes serious when multiplied across thousands of years. The population would also need medical care, genetic diversity, education, and stable methods of government. Technical knowledge could not remain confined to manuals. Each generation would need enough trained engineers and doctors to keep the habitat functioning before teaching the next generation. Language would change naturally over time, just as Latin gradually developed into several modern European languages. Mission records would require regular translation, so their meaning remained clear. Suspended animation could reduce many of these demands if human metabolism could be slowed safely. NASA-funded studies have examined torpor for journeys lasting months, particularly possible missions to Mars. Torpor is a state of reduced body temperature and metabolism seen naturally in some mammals. Humans do not enter deep reversible hibernation on their own. Medicine can cool patients for limited periods during certain procedures, but preserving a healthy person for centuries and restoring them without brain or organ damage remains beyond present science. Every human survival system adds mass. Food production needs lamps and growing chambers. Artificial gravity requires a large rotating structure. Radiation protection demands thick materials surrounding living areas. The vehicle becomes harder to accelerate as it becomes more capable of preserving life. Physics does offer one way for travelers to experience less time without shortening the journey measured from Earth. At velocities close to the speed of light, the clock aboard the spacecraft would begin to separate from the calendar left behind. Special relativity allows the duration aboard the spacecraft to differ from the duration measured on Earth. Both clocks would behave normally for the people beside them. A second aboard the ship would still feel like a second. Heartbeats, meals, sleep, and aging would continue at their usual pace. The difference appears when Earth and the spacecraft later compare how much time passed. Albert Einstein described this effect in 1905. His theory begins with a strange but well-tested fact. Every observer measures light moving at the same speed, regardless of how quickly the observer is traveling. Space and time adjust to preserve that result. As the spacecraft approaches the speed of light, Earth observes its clock running more slowly. The travelers describe the same journey differently. From their perspective, the distance ahead becomes shorter in the direction of motion. This shrinking of measured distance is called length contraction. Consider a ship cruising at 99% of light speed. It would travel at approximately 297,000 kilometers per second. Earth would measure about 26,263 years for the ship to cross 26,000 light years. That simple estimate assumes the craft is already at cruising speed and does not include the time needed to accelerate or brake. The travelers would experience about 3,705 years during the cruise. The difference comes from a number called the Lorentz factor. At 99% of light speed, the Lorentz factor is approximately 7.09. Dividing the Earth frame travel time by that factor gives the shorter duration measured aboard the ship. 3,700 years still exceeds a human lifetime. Greater speed makes the difference much stronger. A useful thought experiment gives the crew a constant acceleration equal to Earth's surface gravity. This is usually called one gravity. The ship would accelerate toward the galactic center for the first half of the journey. At the midpoint, it would rotate so its engines faced forward. The same one gravity thrust would then slow the craft during the remaining half. Inside the ship, that acceleration could also create a sensation similar to standing on Earth. The floor would press upward against the crew as the engines pushed the spacecraft forward. Under this idealized profile, the people aboard would experience about 19.8 years between departure and arrival. Earth would measure approximately 26,002 years. A person leaving at age 30 could theoretically arrive before turning 50. Earth would pass through more than 26,000 years of history during the same journey. The two clocks disagree because the ship spends most of the crossing at a speed extraordinarily close to light. At maximum velocity, it would travel within 300 millionths of 1% of the speed of light. At that point, adding more engine power produces very little additional speed. Most of the added energy increases the relativistic energy of the spacecraft. The engineering demands become extreme. Maintaining one gravity for nearly 10 shipboard years during acceleration would require a propulsion system capable of operating continuously at immense power. The ship would then repeat the process while braking. Its fuel or energy source would need to support both halves of the journey. Waste heat would have to leave through radiators throughout the powered flight. Particles ahead of the ship would arrive with energies far beyond those discussed at 20% of light speed. Even thin interstellar hydrogen would strike the forward shield as intense radiation. A dust grain could release catastrophic energy before any navigation system had time to respond. The 19.8-year result therefore belongs to a physics calculation rather than a construction plan. It shows what relativity permits when acceleration and energy are treated as available. It does not show that humanity knows how to build the engine, shield, or power system required to perform it. The calculation still changes the human meaning of the journey. A crew could experience the crossing within its own adulthood, while every person and institution known at departure disappeared into Earth's distant past. Those passing millennia would also give future civilizations time to improve propulsion. A slower ship launched first could remain in transit when a later vehicle left Earth and overtook it. That possibility creates a strange problem for any civilization planning a journey this long. A spacecraft leaving Earth at 1% of light speed would travel almost 3,000 kilometers per second. Even at that speed, the 26,000 light-year crossing would take about 2.6 million years. Now imagine that the first ship departs in 2026. Its engines work as planned. Its navigation system remains stable. The craft begins the slow passage inward through the Milky Way. Much later, Earth develops a propulsion system capable of reaching 10% of light speed. The second spacecraft would travel almost 30,000 kilometers per second and complete the same basic crossing in about 260,000 years. That faster mission saves roughly 2.34 million years of cruise time. Earth could wait more than 2 million years before launching it and still allow the second spacecraft to reach the galactic center first. The exact result would depend on acceleration, braking, route length, and the motion inherited from the solar system. The simple comparison assumes both ships settle into constant cruise speeds along similar paths. Its larger point remains valid. A sufficiently large increase in velocity can overcome an enormous delay in departure. This effect is sometimes called the waiting paradox. A civilization must decide whether to launch with the best technology currently available or remain home while propulsion improves. Launching early begins the journey sooner. Waiting may produce a vehicle that erases the early advantage within a small fraction of the total travel time. The first ship could continue for hundreds of thousands of years before detecting the later mission. Its instruments might notice a fast object approaching from behind. A laser message could arrive first, explaining that a new spacecraft had left Earth long after the original departure. The overtaking craft might pass at a large distance to avoid damaging either vehicle with exhaust, radiation, or disturbed dust. From the first ship's point of view, the encounter could last only briefly. The later vehicle would then move ahead and gradually disappear towards Sagittarius. A crew aboard the original ship might eventually receive reports from the destination. The faster mission could map the nuclear star cluster, establish communication beacons, or prepare a safer route through the central region before the older ship arrived. A voyage once expected to become humanity's first expedition to the galactic center would approach a destination already studied by travelers from a much later age. The same outcome could affect an autonomous probe. Its original instructions might tell it to perform the first close survey of Sagittarius A star. Millions of years into the mission, incoming transmissions could reveal that newer machines had already completed the task. The probe would then need to decide whether its remaining scientific purpose justified continuing unchanged. That decision becomes especially complicated when the vehicle has replaced most of its original hardware and updated its software countless times. Waiting carries its own risk. Technological progress does not follow a guaranteed upward path across geological time. Homo sapiens has existed for roughly 300,000 years. Agriculture began only around 12,000 years ago. Powered flight is little more than a century old. A delay of even several thousand years extends far beyond any period for which industrial civilization has demonstrated continuity. A society may lose the resources needed for interstellar travel. Political priorities may shift. Environmental change, war, disease, or technological collapse could end the program before the faster ship is ever built. An early mission moving at 1% of light speed might become the only spacecraft launched, while the necessary knowledge and infrastructure still existed. Its slow progress would then preserve an opportunity that waiting had allowed Earth to lose. Departure time and arrival time therefore become separate choices. The first launch may secure the journey. A later launch may secure priority. No calculation made in 2026 can reveal which civilization will still exist millions of years later, or what propulsion it will command. Whichever craft eventually reaches the inner Milky Way will encounter the same broad transformation. The widely spaced stars around the Sun will give way to the crowded orbits, stronger radiation, and increasingly complex gravity of the galactic bulge. By the time the spacecraft entered the inner 10,000 light-years of the Milky Way, the route would begin to look very different from the region around the Sun. The Orion Spur and the broader spiral disk contain long stretches where neighboring stars are separated by several light-years. Near Earth, Proxima Centauri lies about 4.24 light-years away. In the central regions, some stars may be separated by only 0.4 light-years. The spacing can fall to roughly 0.04 light-years inside the densest parts of the nuclear star cluster. That smaller distance is still about 380 billion kilometers, but it is tiny compared with the gaps surrounding the solar system. The familiar spiral pattern would gradually give way to the galactic bulge. NASA describes this transition as occurring across roughly the inner 10,000 light-years. The bulge is a thick concentration of stars surrounding the central region. Many of its stars are old, although younger populations and active star-forming areas also appear closer to the nucleus. The bulge does not rotate like one solid object. Its stars follow a wide range of paths through the galaxy's gravitational field. Some move above and below the main disk. Others travel along stretched or tilted orbits that carry them toward the inner region and then back outward. These motions are shaped partly by the Milky Way's central bar. The bar is an elongated structure made from stars and gas extending across the middle of the galaxy. Viewed from above, it would resemble a bright band passing through the central bulge. The Milky Way's spiral arms begin near the ends of this bar, rather than emerging from a perfectly circular center. A round mass distribution tends to support nearly circular orbits. An elongated bar applies gravitational pulls that change direction as stars and clouds move around it. Gas can be guided along long curved streams. Some material loses orbital energy through collisions and turbulence, allowing it to drift inward. Other clouds become compressed near the ends of the bar, where gas enters the inner spiral structure. For the spacecraft, this means the route can no longer be described as movement through a calm set of broad circular lanes. Stars cross the region along paths with different angles and speeds. A star predicted to remain safely distant may pass closer after thousands of years of accumulated gravitational changes. The craft would need to update nearby trajectories continuously, rather than rely on simple long-term projections. Relative speeds also rise in the inner galaxy. Near the Sun, many neighboring stars share broadly similar motion around the galactic center. Inside the bulge, their orbits are more varied. Two stars can pass one another while moving in sharply different directions. The chance of an actual collision remains extremely low because even this crowded region contains vast amounts of empty space. The number of close passages would still increase compared with the solar neighborhood. Sagittarius A star becomes more important as the craft approaches the final few light years. Its mass is approximately 4 million times that of the Sun. That sounds large enough to control the entire galaxy. Yet the Milky Way contains hundreds of billions of stars, along with enormous amounts of gas and dark matter. Across most of the disk, their combined gravity outweighs the pull of the central black hole. The Sun's galactic orbit is governed mainly by the total mass distributed throughout the Milky Way. Sagittarius A star dominates the motion of objects only within the innermost region around the nucleus. Farther out, it contributes only a small part of the gravitational field. The spacecraft would therefore pass through several layers of influence. The broad galaxy would first guide its motion. The stellar bulge and central bar would then reshape the route. Only near the end would the black hole begin controlling nearby orbits directly. The stars would continue growing denser as the ship moved inward. But the next major change would come from material between them. Inside the bulge lies a gas-rich region where molecular clouds, magnetic fields, and energetic radiation become heavily concentrated around the center. Gas flowing inward through the Milky Way's bar gathers around the nucleus in a region called the central molecular zone. This zone extends across the inner several hundred light years of the galaxy. It contains some of the densest concentrations of molecular gas in the Milky Way. Molecular gas is cold enough for hydrogen atoms to join in pairs. These clouds also contain helium, dust grains, and small amounts of heavier molecules formed from elements such as carbon, oxygen, and nitrogen. The central molecular zone holds only a small fraction of the galaxy's total volume. Its clouds contain a large share of the dense gas found near the center. Gravity from the bar guides material inward along stretched paths. Clouds collide, compress, and move through strong magnetic fields. Their internal gas can be highly turbulent, meaning it contains irregular motion at many different speeds and directions. A major example lies only a few hundred light years from Sagittarius A star. It is called Sagittarius B2. NASA describes Sagittarius B2 as the Milky Way's most massive and active star-forming molecular cloud. The cloud contains approximately 10% of the gas found in the galactic center region. It produces roughly half of the stars forming there. Sagittarius B2 is not one smooth object. It contains dense cores, hot regions surrounding young stars, and extended clouds rich in complex molecules. Radio telescopes have detected alcohols, sugars, and other carbon-based compounds inside it. These molecules do not indicate life. They show that complicated chemistry can develop inside cold clouds before planets have even formed. Many stars inside Sagittarius B2 remain hidden at visible wavelengths. Dust absorbs their light. Infrared and radio observations can pass through more of that material and reveal warm gas, young stars, and compact regions where massive stars are beginning to shine. Those young stars alter the cloud almost immediately. Ultraviolet radiation heats and ionizes nearby hydrogen. Stellar winds push gas outward at high speed. The most massive stars may explode after only a few million years, sending shock waves back through the surrounding material. Another cloud complex, Sagittarius C, lies roughly 200 light-years from Sagittarius A star. Images from the James Webb Space Telescope reveal a field spanning about 50 light-years. The view contains young stars, glowing hydrogen, and long structures shaped by magnetic fields. Charged particles in the gas follow those fields, creating organized filaments inside a region that otherwise appears chaotic. Magnetism can slow the collapse of some clouds, while guiding gas into denser concentrations elsewhere. This helps explain why star formation across the central molecular zone is uneven. Some clouds hold enormous amounts of dense material, while producing fewer stars than expected. Others form clusters containing many massive young stars. A spacecraft moving near relativistic speeds would treat these clouds as major hazards. The gas density inside a molecular region can exceed the surrounding interstellar medium by many thousands of times. Dust impacts would become more frequent. Hydrogen atoms striking the shield would arrive as energetic radiation. Young massive stars would add ultraviolet light, charged particles, and powerful stellar winds. Supernova remnants could place expanding shock fronts across parts of the route. The safest path would curve around the densest clouds. Long-range infrared and radio instruments would map the material ahead. The navigation system could compare several possible corridors, balancing added distance against impact damage and radiation exposure. Even a detour of dozens of light-years could be worthwhile near the end of a journey lasting more than 100,000 years. Sagittarius A star would remain hidden behind these active surroundings until the spacecraft passed beyond the thickest clouds. The final destination would already feel larger than a single black hole. It would include turbulent gas streams, young stellar clusters, and magnetic structures extending across hundreds of light-years. Past the central molecular zone, the star field would compress again. The spacecraft would be entering the nuclear star cluster, the most massive and densely packed star cluster in the Milky Way. Beyond the densest gas clouds, individual stars would begin to dominate the view. The spacecraft would enter the nuclear star cluster surrounding the center of the Milky Way. This cluster is the most massive and densely packed stellar cluster in the galaxy. Visible light telescopes struggle to study it because thick dust lies between Earth and the center. Infrared light passes through much more of that dust. Using infrared observations, the Hubble Space Telescope revealed more than 500,000 stars inside a central field. Many more remain too faint, crowded, or hidden to count separately. The density would change the appearance of the sky. Near the Sun, the closest star system is Alpha Centauri, more than 4 light-years away. Inside parts of the nuclear cluster, neighboring stars may be separated by only 0.4 light-years. In the most crowded regions, the gap can shrink to about 0.04 light-years. That is roughly 100 times closer than Alpha Centauri is to the Sun. NASA has compared the central density to placing as many as 1 million suns inside the volume between the Sun and Alpha Centauri. Those stars would not all look identical. Cool red giants would glow through the infrared. Hot young stars would shine strongly in ultraviolet light. White dwarfs, neutron stars, and stellar mass black holes would remain as compact remnants of earlier generations. Dust would still hide parts of the scene, but the darkness would be filled with sources lying behind it. Two major young clusters stand within about 100 light-years of the galactic center. The Arches cluster is one of the densest young star clusters known in the Milky Way. It contains many massive stars packed into only a few light-years. Some of those stars are dozens of times more massive than the Sun and produce far more light during their short lives. Their ultraviolet radiation strips electrons from nearby gas. Powerful stellar winds carry matter outward at speeds of thousands of kilometers per second. The quintuplet cluster lies nearby and contains another large population of massive young stars. Its name came from 5 bright infrared sources that stood out in early observations. Later studies showed that the cluster contains far more than 5 stars. Several are nearing the ends of their lives and have already shed large amounts of material into the surrounding region. For the spacecraft, this crowded sky would create hazards from many directions. The forward shield would still absorb gas and dust encountered along the route. Radiation would arrive from stars scattered throughout the surrounding cluster. Ultraviolet light could degrade exposed materials. Charged particles from stellar winds would follow local magnetic fields and strike different parts of the craft. A nearby supernova would send intense radiation and a rapidly expanding shell through the region. Direct collisions with stars would remain extremely unlikely. Even here, the distances between them are enormous compared with the size of the stars themselves. Close gravitational encounters would become more common, however, and every nearby passage could alter the ship's path slightly. Navigation software would track thousands of moving objects at once. Some stars would pass across the route. Others would curve around the nucleus on steeply tilted orbits. Compact remnants might remain difficult to detect until their gravity revealed them. The simple design of one thick forward shield would no longer cover every important threat. Sensitive systems might need protection on all sides. Radiators, communication equipment, and telescopes would require movable shielding or the ability to retract behind the hull. The ship would have entered a region where light, gravity, and energetic particles surrounded it continuously. The hidden center, seen from Earth as a dark lane, would now appear crowded with more starlight than any sky near the solar system. Within that dense field, several stars would move fast enough to stand apart. Their paths would bend sharply around an invisible point, tracing the mass of Sagittarius A star with every orbit. One of the clearest guides is a star known as S2. It belongs to a group called the S stars, which move around Sagittarius A star on tight, fast orbits. S2 is much more massive and hotter than the Sun. From Earth, it appears as a point of infrared light buried among many other stars near the galactic center. Its movement has been followed for more than 25 years by telescopes, including the Very Large Telescope in Chile and the Keck Observatory in Hawaii. S2 completes one orbit in approximately 16 years. The path is highly elliptical, meaning it is stretched rather than circular. For much of each orbit, the star remains relatively far from the center. It then accelerates rapidly as it approaches periapsis, the closest point in its path. During its 2018 passage, S2 came within about 20 billion kilometers of Sagittarius A star. That distance is around 120 times the average distance between Earth and the Sun. It sounds large until it is compared with the mass concentrated inside the orbit. At closest approach, S2 traveled at nearly 3% of the speed of light. Its velocity reached roughly 7,600 kilometers per second. At that speed, the star could cross the distance between Earth and the Moon in less than 1 minute. The changing motion of S2 allows astronomers to measure the central mass without seeing the black hole directly. A star's orbital speed depends on the gravity pulling it inward. Its curved path also shows where that gravitational force is centered. By recording S2's position and velocity over a complete orbit, astronomers can calculate how much mass must exist inside it. The answer is close to 4 million times the mass of the Sun. That mass is confined within a region small enough to rule out ordinary alternatives, such as a dense cluster of faint stars. A cluster containing millions of stellar remnants would collide, scatter, or collapse over astronomical time. The observed system remains compact and stable in the way expected for a supermassive black hole. S2 also provides a test of gravity under conditions far stronger than those found around the Sun. In Newton's description of gravity, an isolated star would repeatedly trace almost the same closed ellipse. Einstein's general theory of relativity predicts a small additional change. The closest point of the orbit shifts forward after each circuit. This effect is called Schwarzschild precession. The name refers to the curved spacetime surrounding a spherical mass. Astronomers detected this shift in S2's orbit. Its periapsis advances by about 12 arc-minutes during each 16-year circuit. An arc-minute is 1/60th of a degree. Repeated over many orbits, the path would form a rosette-like pattern, with each ellipse turned slightly relative to the one before it. Mercury shows the same basic effect around the Sun, although the shift there is far smaller. Near Sagittarius A star, the stronger gravitational field makes the change easier to measure across a human lifetime. The light from S2 also changes as the star moves through the deepest part of the orbit. Gravity and high velocity stretch its light toward longer, redder wavelengths. Observations during the 2018 passage matched the change predicted by relativity. For the arriving spacecraft, these stars would serve as moving markers around the destination. Their paths would reveal the black hole's mass, location, and local gravitational field with extraordinary precision. The vehicle could compare its own measurements with orbital records begun on Earth tens of thousands of years earlier. Sagittarius A star would no longer be a hidden radio source at the end of a map. It would be the central mass guiding visible stars through measured curves directly ahead. Reaching that neighborhood would still leave the spacecraft moving at an immense speed. Without a long and carefully timed braking phase, it could cross the entire central system in hours and continue out through the opposite side. A spacecraft approaching the galactic center would still need to decide what arrival actually meant. The central region has no single boundary marked by a line in space. Entering the inner 1,000 light-years would place the craft inside the broader galactic bulge. Passing into the nuclear star cluster would bring it among the densely packed stars surrounding Sagittarius A star. Reaching the central parsec would carry it within about 3.26 light-years of the black hole. A controlled orbit near Sagittarius A star would demand far greater precision. Crossing the event horizon would be a completely different outcome. The event horizon is the boundary beyond which light cannot escape. Any spacecraft passing through it could no longer send information back to the outside universe. That makes the horizon a poor scientific destination for a mission intended to report what it finds. The practical finish line would probably be a stable orbit around the black hole, a nearby star, or another well-measured point inside the nuclear cluster. Reaching that orbit requires the spacecraft to match the speed and direction of local motion. A ship arriving at 20% of light speed would still be moving at nearly 60,000 kilometers per second. The black hole's gravity could bend that path. It could not automatically remove the enormous energy carried by the spacecraft. Without a braking system, the vehicle would pass through the central region and continue outward on the opposite side. At 20% of light speed, it would cross 10 light-years in about 50 years. The densest few light-years near Sagittarius A star could pass in only a few decades. A smaller scientific target might remain within useful range for days or hours. The journey would become a flyby, rather than a lasting arrival. Deceleration would therefore need to begin long before the black hole filled the forward view. The spacecraft might reverse its main propulsion system and spend years reducing speed. A beam sent from infrastructure already built near the center could push against a sail from ahead. Magnetic systems might interact with charged particles in the surrounding plasma, although the available braking force would depend on local density and field strength. Every method must dispose of almost the same kinetic energy used to accelerate the craft at departure. The final orbit would also need to avoid the most active material around Sagittarius A star. A ring of ionized gas and warm dust surrounds the central region. NASA describes this circumnuclear ring as roughly 10 light-years in diameter. Circumnuclear simply means that it lies around the nucleus. The ring contains clumps, streamers, and material moving through the black hole's gravitational environment. Closer to Sagittarius A star, hot gas and stellar winds flow inward from nearby stars. This material forms a faint, variable, magnetized accretion flow. Accretion is the process in which gas loses energy and moves toward a massive object. Sagittarius A star currently consumes very little compared with the most active black holes in other galaxies. Chandra X-ray observations indicate that less than 1% of the gas entering the black hole's wider gravitational influence reaches the event horizon. Much of the material is pushed away, heated, or prevented from falling directly inward. The result is still a difficult operating environment. Gas density changes across short distances. Magnetic fields twist through the flow. Radiation levels rise during flares, when the region near the black hole brightens temporarily in X-rays and infrared light. A safe scientific orbit would remain far outside the event horizon and away from the densest gas streams. From there, the spacecraft could observe stellar orbits, magnetic fields, hot plasma, and the shadow of Sagittarius A star over many years. The black hole contains about 4 million solar masses, so even distant orbits would move through a strong gravitational field. The craft would adjust its path repeatedly as nearby stars and gas altered the local conditions. After 26,000 light-years of travel, the mission would depend on one final controlled change in velocity. Survival across the galaxy would matter only if the spacecraft could slow enough to remain. With that requirement included, the answer can finally return to a departure from Earth in 2026 and compare the arrival dates produced by each major form of travel. The completed journey can now be traced back to a departure from Earth in 2026. Each arrival date depends on the speed, acceleration plan, payload, route, braking method, and chosen finish line. Light provides the absolute limit. A beam leaving Earth in 2026 would need approximately 26,000 years to reach Sagittarius A star. It would arrive around the year 28,026. The idealized one-gravity journey produces a similar date on Earth. A spacecraft accelerating at one Earth gravity for half the distance and decelerating at the same rate for the remaining half would arrive after approximately 26,002 Earth years. That places the arrival around the year 28,028. The travelers aboard would experience only about 19.8 years. Someone leaving Earth at the age of 30 could theoretically reach the galactic center before turning 50, while more than 26,000 years passed at home. A ship cruising at 99% of light speed would take approximately 26,263 years according to Earth's clocks. Departure in 2026 would produce an arrival around the year 28,289. The travelers would experience approximately 3,705 cruise years. That estimate excludes whatever additional time the ship requires to accelerate and brake. At 20% of light speed, the journey would last about 130,000 years. The spacecraft would arrive around the year 132,026. Its Milky Way would remain broadly recognizable. Many stars would occupy different positions, while clouds near the center would have collapsed, dispersed, or produced new generations of stars. A craft maintaining 10% of light speed would require approximately 260,000 years. Its arrival would fall around the year 262,026. At 1% of light speed, the crossing expands to about 2.6 million years. Departure in 2026 would lead to an arrival around the year 2,602,026. Massive stars visible at launch would have completed their lives many times over through later generations. Young clusters would disperse, and the original galactic map would become a record of an ancient stellar arrangement. Present spacecraft speeds create far longer journeys. Using the Parker Solar Probe's record velocity, as though it could be sustained continuously, produces a travel time of approximately 40.5 million years. Parker reaches that velocity only during close approaches to the Sun, so the figure serves as a speed comparison rather than a mission plan. Using Voyager 1's outward speed gives approximately 458.5 million years. The solar system completes one orbit around the Milky Way in roughly 230 million years. The Sun would circle the galaxy almost twice during the equivalent Voyager crossing. Sagittarius A star would probably remain the dominant central object, while the surrounding clouds, clusters, stellar remnants, and gas streams belong to a much older Milky Way. These timelines describe different travelers and different missions. A gram-scale probe could accelerate more easily than a vessel carrying people, farms, radiation shielding, and repair factories. A brief flyby would require less braking than a controlled orbit. Route changes around molecular clouds would add distance. Near light speed, the time experienced aboard would separate dramatically from the history unfolding on Earth. Even successful arrival would remain unknown at home for another 26,000 years. A confirmation signal sent after the light speed benchmark arrived around the year 28,026 would reach Earth near the year 54,026. News from the 20% light speed mission would return close to the year 158,026. Departure, arrival, and confirmation would become three separate moments divided by immense stretches of history. The light reaching Earth from the galactic center tonight began traveling about 26,000 years ago. It left while humans were living near the end of the last ice age. A spacecraft launched beside the Sun in 2026 would travel toward the place that ancient light came from. It could arrive after 20 experienced years, after thousands of shipboard years, after hundreds of thousands of Earth years, or after nearly 500 million years. Once the spacecraft entered a controlled orbit around Sagittarius A star, it could send a message announcing that the journey had ended. Earth would wait another 26,000 years to receive it.